What about this? Let's take this back down to zero, not to zero, to 1, and increase the product concentration. If this is 1, then, but these are 2 molar. Will it still be spontaneous in the forward direction? I'm going to contend that yes. This is a spontaneous reaction. It is going to go from left to right spontaneously. That means the other direction is not spontaneous. But what if we're product heavy? It's going to go to the right with a lower voltage. There's not as much push to get the electrons from the anode to the cathode. So when the reaction is spontaneous but it's product heavy, that means that it's kind of opposing the direction. It still goes to the right, but with less force, with less voltage. Now we're going to quantify that. I've got a derivation on the next slide. So as a reaction occurs, remember this was spontaneous in the forward direction. So as it goes forward, the concentration of reactants is going down and products is going up, right? And as that happens, the voltage, and you can kind of see this happening, the voltage is going down. The more products you have, the less push the electrons are going from the anode to the cathode, and so the lower the voltage. That's what happens when batteries die. Batteries die because the reaction that's happening inside the battery becomes so product heavy, so you have such a low concentration of products and a high concentration, sorry I said that wrong, such a low concentration of reactants, so a little bit of that left, and such a high concentration of products, that yes, the electrons may still tend to flow from anode to cathode, but the voltage has gone down so much it can't power your device. Yes?
So the E cell is still increasing, but at a lower rate?
No, E cell would be decreasing.
Okay.
It starts high, but then as the reaction proceeds, it goes down, down, down. It just keeps going down. Yep. Here's how we find the cell potential, the epsilon cell potential, if we're not in standard conditions. If you are in standard conditions, use the table and you're good. You're done. But if you're not, we have to derive it. And we're going to begin with this equation. And you've seen that before in chapter 17, the thermodynamics. Whose equation is this? Who came up with this one? Anybody want to take a stab at this? Wrong.
It was Gibbs.
Right. Nilesh? Right.
Oh.
I know that we've got another equation associated with Gibbs, the delta H minus T delta, as we call that the Gibbs free energy equation. But this is also an equation that Gibbs developed and came up with. So yeah, he said that delta G at any point in the reaction equals the standard delta G, that's only in standard conditions, plus RT ln of Q. Remember what Q is? Q is the ratio of products to reactants, but not necessarily at equilibrium. It could be at any point in the reaction. Yeah. Capital Q, I think, though, is pretty set as just one quantity. It's Q because it's called the reaction quotient. It's that ratio of products to reactants.
Why is lowercase q?
I have nothing.
Why did they just use a lowercase h?
Yeah, why not H? Well, they use H for Planck's constant.
Why did they use p?
Why they should use P, yeah. Maybe they're already using P for power in physics. You learn about power, right? So yeah, I don't know. There's just too many quantities and only 26 symbols. And then they go to the 24 Greek letters too. You'll get to college, a lot of your professors are going to use Greek letters for symbols for things. I don't know. What's that? Oh, right. Yes, that's right. What's happening?
Like a squid.
Stephen, that is not an octopus, it's a banana.
It's an octopus.
All right, what do we do now that we've learned something about delta G in this chapter? Delta G equals negative NF epsilon. So we're going to do a little substituting. Since this is true, then we're going to just replace the delta G with negative NF epsilon. And then it's the standard delta G, so it's negative NF epsilon standard. That's the table value, plus RT ln of Q. Remember, we're trying to find the cell potential if we're not at standard conditions. This thing refers to any point in the reaction what the delta G is. And now we have a hook between epsilon and delta G. So that's what we're going to just do some algebra and get the cell potential on its own at any point in the reaction. Now the next thing that we're going to do is we need to get the cell potential on its own. So divide out the negative NF. Well, it'll be gone from that term and gone from that term, so the only place it shows up is negative NF is going to be over there, looking like this. Doesn't matter what order you do multiplication and division in. So I just kept all these other terms out here in the ln of Q at the end. Now there's just one more cleanup step. What do you see right here? Some constants? Let's just replace the constants with the numbers that they are for. The temperature, we're always going to use 25 degrees, unless I tell you otherwise, which I don't think I will. The temperature is going to be 25 degrees for all these reactions. So we're just going to plug in 298 Kelvin for that T. The R is 8.31, the thermodynamic constant. And F is Faraday's constant. So I have constant, constant, and constant. Let's just go ahead and put the numbers in for those, and we don't have to worry about remembering what they are. And then also, and I don't know why he did this, but the guy that came up with this equation, he changed the natural log into log base 10. So when I go down a little bit, you're going to see it has changed to log. Now, there is a conversion between natural log and log log. It's natural log times 2.303 equals log base 10 of any number. Have you learned that before? The connection between those two? I bet you have when you did logs. But here's what it is. So RT and F have all been replaced by their numbers, and it gives us 0.0591. And then we still have N, because N is a variable. N depends on the reaction, how many moles of electrons are transferred. And then you see how the log has changed to log base 10. So R times T times, or over F, and then times 2.303 is how we come up with that number. And this is as long as we're at 25 degrees Celsius, we can always use this equation. The equation has a name. It was named after the guy that derived it. And he's got the best physics name ever.
Jim.
His name was Nernst. Chemistry people are cool. You never find a chemistry person with a geeky name, but physics? Is that not a physics name? Nernst. He was destined for physics, and he actually did something good.
Sounds like something like throughout.
Maybe so.
Sounds like it's
So-
throughout when they were naming him.
So you're going to use the Nernst equation if you need to find a cell potential, a voltage, but you're not at standard conditions, which is almost all the time. This is how we find it. Remember, Q, that's products over reactants. So if a reaction is reactant heavy, what does that mean about the cell potential? Reactant heavy means that we're very heavy, and that means the reaction is full of reactants. And what does that say about the cell potential? Well, reactants is in the denominator here, which makes that fraction smaller. What happens to log of a smaller fraction.
Next equation.
The log becomes smaller, and we're subtracting it. So we're subtracting a smaller number. What does that mean about the voltage?
Gets bigger.
It goes up, it gets bigger. Right. So the Nernst equation actually provides the rationale for why it is. We were using Le Chatelier's principle over here, but you could also think of it, now that we see the Nernst equation, it still illustrates the same concept. The Nernst equation. I have a homework assignment for you tonight. I expect you to do it. I want you to go home tonight and find in the end of the chapter exercises, there's a section that says the Nernst equation. I want you to do one problem in the Nernst equation.
That's it.
Yeah? Nope, not for grade.
But that's the only one you want us to do.
It's one problem, Showbiz. It's a plea. I've got a plea for homework.
Is that the only one you want us to do?
Is it what?
Is that the only one you want us to do? Or do you want us to
No, I mean, you will want to do a few. But if you can remember, hold on. It's chapter 18, right?
Is there any nerves
Your son. Your son.
Don't talk about
Starting at number 67.
No.
I can do what I
Whatever
want.
homework is assigned just after number 67, maybe 67 is one of them. Just do one. One Nernst problem.
Shaquita.
Because we're going to start with those tomorrow. I want you to know how to do it.
Can you use HF?
Oh my god, there's like
Are you serious?
I was
Yes,
totally-
you can use HF.
Okay. Let's do it. Alright, but it goes in the hardware store to get it done.
Yeah, you might have a hard time finding it.
You like, go on about it.
Go on.
No.